Okay, so today we will talk about the bias variance trade-off. You will hear about it a lot, and it's a fundamental concept important to know. This is from the ISLR book. So what is the bias variance trade-off? Imagine you have these observations, these circles. These are the observations. And then you have this underlying trend, which is um, the black curve. So we assume that this underlying trend exists. It's like the population parameter. It's equivalent to the population parameter. When you use a sample mean to estimate the population mean, it's the same here in the sense that you have this population curve or vector that we like to estimate. We don't see it. We see a noisy version of it, which are these circles. Some of them are above it, some of it are below it. And based on these circles, we want to estimate this trend. Now what happens is typically we have a family of methods at our disposal. And this family of methods, they typically have a tuning parameter, at least one, sometimes more. And a recurrent question that any data analyst or anybody who's trying to do some sort of modeling or to find some pattern needs to um, basically know the answer to or have an answer for is what is the right level of tuning, and that tuning parameter changes fundamentally the result. On the one hand, we can get a line. A line is not flexible. A line is straight. A line doesn't accommodate curves. It's either going up or down at a certain angle. That angle is fixed all through. So it's a simple model. On the other hand, we can have this very flexible green curve, or even blue one, or green, which is trying to pass through as many or as close as possible to the points. It's very flexible, and it uh, captures the nuances in the data. Whether that's a good thing or a bad thing is the big question, because nuances in the data could be just idiosyncrasies of the noise. This circle happened to be above this curve, this population. It could have been below it, and if it was below it, then this green curve probably would have gone down. So here we're modeling noise. No, we don't want that. We care about the data only as much as it tells us something about this population parameter or vector or signal or pattern, whatever. Here it's the black curve. One such family are the smoothing splines, which we will talk in chapter 6 about. No, actually not chapter 6, it's oh, it's here. Chapter 7. Um, chapter 7.5 of the ISLR book. And here I just give you a very short flavor of what a smoothing spline is. In fitting a smooth curve to a set of data, what we really want to do is find some function g of x that fits the observed data well. That is, we want the residual sum of squares to be equal the sum to be small. So this we want to be small. So what does this mean? Yi are our observations, and xi, I mean, essentially we observe yi's and xi's. For example, this is the car example from the ISLR library, and this is a summary of the data: mile per gallon, cylinders, displacement, horsepower, weight, acceleration, year, origin, name, etc. Okay, and we are looking at the response for us. Y is mile per gallon, and then we take the fourth column, which is horsepower, as our predictor. So horizontal axis is horsepower, vertical axis is mile per gallon, and we want to use horsepower to predict mile per gallon. We want to see what's the underlying relationship. And let me just clean this up. Yes, I want to remove this. I want to remove all of them. Okay. We haven't done. Okay. But this is like the real data set. This is like this graph, to be a proper graph, needs to have a label on the vertical side, and on the horizontal side, the vertical side should be wait a second, are we doing it should be the other way around. Okay, so vertical axis is mile per gallon, mileage per gallon, and vertical axis is mileage per gallon, horizontal axis is horsepower, and we want to see what is that relationship. And so that's that. That's the example. Now, okay. So these are the xi's and the yi's. Now we want to find the function g. It can be a curve, it can be a line, whatever, that at those locations is close. So the residual sum of squares is small. Now, obviously, we can make this as small as we want by simply saying g being equal to y. But that is just raw data. We want some regularity, and that regularity is the pattern. We want it to be a line, or we want it to be exponential, or we want it to be a curve that goes going down. Our underlying assumption is whatever the relationship between g and x is, between mileage per gallon and horsepower is, that relationship is a smooth function, maybe smooth decreasing. Maybe it's smooth going down and going a little bit up and down, but that's it. It's not wiggly. And how do we capture that belief? Well, instead of saying we are looking for a g function that only makes this as small as possible, we are looking for a g function that, yes, makes this as small as possible, but is also smooth. And smoothness is measured with the second derivative squared integrated over the whole domain. And the trade-off between these two is controlled with this hyperparameter tuning parameter lambda. Okay, but this is just a high level view, and how it translates into R is the next thing I will talk about. So in R, I want to show you how the curves will change as the as lambda changes. So we'll use this function smooth spline. You just give the x's the y's, and then you give it the degrees of freedom. Degrees of freedom is not the lambda, okay? But think of it as something that is a surrogate for lambda, okay? Degrees of freedom are essentially the number of parameters in the model. Like a line is defined by 2 parameters. A quadratic curve with 3 parameters. So here we start with the 3, you go to 40. The more parameters you have, the more likely is it that the curve will pass through all these data points. Okay. Let's look at this. So this is a general curve, but then these things happen too. So what are they? Are they just outlying noise happen to just be a little bit higher? Or does that represent a pattern? Something that's meaningful, something that we can get some insight, or something that can happen tomorrow, the next car that comes out? That's the type of questions we like to answer. Of course, it's going down, but then it's just, let's just show you what happens. So here we have a for loop. This for loop goes over goes from j, from 1 to length of ds. ds stands for a vector of the degrees of freedom, and it's 3 to 40. So it's 3, 4, 5, 6, 7, 8, 240, that range. Okay. And we want to go over all of them. And for any of those degrees of freedom that are in this vector, we want to get the corresponding smoothing spline, which gives us this object fit. Then we will just plot the raw data in red. Then we will draw a curve based on the smoothing spline. Right? We get the x values from the smoothing spline, we get the y values, and we draw the curve in blue. And then we will title this figure with the degrees of freedom, so we know whatever we're seeing, what the degrees of freedom is. And then here we have a line which waits for us to press enter to see the next degree of freedom, as opposed to just going through all of it in less than a second. Okay, that makes sense? Okay. So you see, this is degree 3. Degree 3 is not a line. It's a quadratic, but the quadraticness is very small. You see it happens here. Why? Because the figure is, the relationship is not, it's not that curved, or it's not quadratic. So, and the degree is 3. Now I click enter. Degree 4. Just change this slowly. As we increase the degrees, the curve becomes more wiggly, becomes more complex, and it tries to capture the idiosyncrasies in this particular data set, and which we do not know. We don't know whether, yes, it should go down and go up, maybe that's something meaningful, or is this just the idiosyncrasy of this specific data set? If we had received another independent data set of the same cars, maybe the numbers would be more or less the same, but the the variability will be different. So we don't want to capture that. We're not interested in the data. We are interested in the data because it allows us to say something about the underlying trend. So anyway, degree, see, as the degrees increase, it becomes more and more and more complex and wiggly. That's it. So that's what's a smoothing spline, and that's what we meant by um, um, by what's happening here. Okay. Now let's talk about what is a bias and what is a variance. Um, imagine y0 being a new data point, x0 and y0 being new data points that we see tomorrow. We have a data set, and based on that data set, we are estimating this function f hat, and tomorrow we get a new data point x0, which we haven't seen, which wasn't used to estimate f hat, and we plug it in here, and then we see how well we do in average squared. Essentially, this is our prediction error tomorrow. We have accumulated a lot of data today. Based on the data that we have received up to today, we create this model f hat, and then tomorrow we get the x zeros, and we want to see how well this model performs on the actual observed y0. Hopefully this is small, so it shows that our model is doing well. If it's large, then that's bad. But it turns out, regardless of what it is, it can be decomposed into three distinct terms, which are mathematically nice, but they also have deep conceptual meanings. Okay. The bias variance trade-off. Okay. So to start this topic, we need to start with the data generating process. And here, we assume that there is this data generating process. Essentially, there's this function f that describes the relationship between y and x. So whenever I say y, here mileage per gallon. And whenever I say x, here horsepower. Okay? So there is this relationship. We want to describe it. We want to learn it. We don't know where it is. We only see yi's and xi's. But we believe that there is this relationship, and it's corrupted by some epsilon i's, which are IID, identically, independently distributed. They have a zero mean, they have a sigma square variance, which we don't know what it is, but we assume that the variance for all the different observations is the same. So the corruption in the signal, the power of it is more or less the same. And they are independent. Okay, so it's just totally random. It doesn't depend on anything. That's the data generating process. So zero mean means the expected value is zero. If the expected value is zero, then the variance is the same as the expected epsilon I squared, because epsilon I, the expected value of epsilon I is zero, so 0 to the power of 2 is 0, so that's it. So at the high level, we have this data D, which is a set of pairs of observations, first car, horsepower, first car, mileage per gallon, etc. to the last car. So this is our data, and we want to do something to this data and learn this f. But we know what we will learn is not going to be that unknown f, which maybe if we had infinite amount of data we could estimate, but since data is limited, we get something which we call f hat. It's supposed to represent the estimate of that unknown function. Now, how do we quantify how well this f hat is? How do we judge it? How do we quantify how well it performs? Well, we could try it on these data points we have, but that will create this will create a problem which is called overfitting, or getting an optimistic view of the performance. We already have used this data to estimate it, so it's not fair. It's like giving the students a practice exam and then the next day test them exactly on the practice exam. Well, that's not a reasonable way of measuring the performance. What you need to do is to create a new exam that follows the same logic and topics and whatever underlying thought that has gone into the course, but different, not exactly the data points that or the questions that were seen. So a new unseen data point that wasn't used to compute f hat. And that data point is not just any data point, it's a data point that comes from the same data generating process. There is an x0, it goes through this function, an independent noise, zero mean variance sigma noise is added, and we see this. And the question is, what is the expected test? Why do we call this test? Because it's a new unseen data point. So the new unseenness of this data point makes this a test MSE as opposed to a train MSE. Okay. So expected value of y0 minus f hat x0 squared will be a reasonable measure of how well f hat is doing. And the only source of randomness that we are here considering is epsilon 0, and this is the data generating process. So as a first step, what we could do is we could just substitute this f x0 plus epsilon 0 here and see what we get. Remember, this epsilon 0 is the irreducible error. It's the error that we will experience in predictions even if we had this f, even if an oracle would give us f, would tell us exactly what this underlying curve would be, there would be still some irreducible error, which is due to the fact that things that go into the mileage per gallon, there are many things that go into the mileage per gallon beyond horsepower. There's only so much that horsepower can tell us. And whatever else determines the mileage per gallon, we just modeled as something random that can sometimes be positive, sometimes can be negative, but it has a more or less limited scope, and the scope here is defined by the variance, a sigma square. So that's just a refresher on the irreducible error. Let's not forget that f hat is a function of the data. So in a way, f hat is independent of epsilon 0. So in a way, f hat is independent of y. And that makes this expectation look the way it looks here. So expected value of y0 minus f hat x0 squared. Instead of y0, we just substitute what the data generating process tells us. It's f of x0 plus epsilon 0. And then we put these two together to get fx0 minus f hat x0 parentheses plus epsilon 0. And then we square it. For the square, we have the expected value of epsilon 0 square. Then we have the expected value of f x0 minus f hat x0 square. And then we have the cross product between these two. Okay, so here's some high school refresher. Um, Essentially, we're using this identity. Okay. So this is sigma square. This measures how close the function f hat is to f, and then here we have the cross product. Now, because f hat depends on the data, and f is not random, so f minus f hat is just a function of the data, which is independent of epsilon 0. So this is independent of this, and then you have, write this down here too. So if from probability, something just to remind you, if x and y are two independent random variables, then the expected value of xy is expected value of x, expected value of y. Okay, so that will give us that this term is 0. So essentially, what remains is just this term and sigma square. So the expected test MSE again is always defined. So whenever we talk about bias, variance, expected test MSE or train MSE, it is at a certain point. And this point, when we're talking about test MSE or bias or variance, is a new unseen data point. It's new, it's unseen, but it comes from the same data generating process as the rest of the data. Okay, so that's the essential assumption. We showed that this can be decomposed into two terms. One is the irreducible error, and the other part which has to do with how close f hat approximates f. Now let's look at this term, or conceptually f hat or estimate being close to the true unknown function. Can we decompose this into two terms? Well, in statistical learning, when we refer to variance, we mean the amount by which f hat would change if we estimated it using a different training data. That comes, there's an S missing here, that comes from the same data generating process. Okay, let's pause here. The amount by which f hat would change if we estimated it using a different training data that comes from the same data generating process. Remember the data we have, and then from the data we get f hat. And the data comes from where? This is the data generating process. Some noise is added to the function. So imagine you create a new data set where another noise is added. The noise has the same distribution, but the specific values might be different. So you create a new data set, and that new data set will be different from the previous data set. It will generally have the same trend, but the variability will be different. And because of that, we will get a different f hat. Now the question is, When we speak about variance in statistical learning, it means that from data to data that comes from the same source, how much is our f hat changing? Ideally, we don't want it to change much. Because if f hat is supposed to capture the underlying trend, it shouldn't depend on the specific data seen, as long as it comes from the same data generating process, as long as it comes from the same source. As long as it comes from the same source, the underlying trend is the same. So if we're trying to estimate the underlying trend, our estimate should also be more or less the same. Obviously, it won't be because the estimate is a function of the data. But if it's a reasonable estimate, the change from sample to sample shouldn't be significant. That's what we mean by variance. Okay. So bias, now on the other hand, we have bias, which refers to the error that is introduced by approximating a real-life problem, which may be extremely complicated by a much simpler model. For example, here, the underlying trend seems to be nonlinear. Life feels nonlinear. So if we use a line to model a nonlinear phenomena, we introduce bias. And as you can see here, the bias depends on for which x are we looking at it. For x's that are in the range between 40 and 80, the model tends to underestimate the true values. It's underestimating. For values around up to 40 in this range, the line tends to overestimate the y value. So there's a bias, there's a tendency. So it turns out that we can write down this part in terms of a bias square and variance square. So if we wanted to study this using a simulation, how would we do it? We would use the law of large numbers, which means that we have the sample mean. The sample mean converges to the population mean as the sample size increases. So sample mean goes to the population mean. Sample variance goes to the population variance as long as the sample size increases. So in a simulation, we would just draw a lot of samples from the same data generating process and then calculate sample variances, sample means, and subtract them, and then we have estimates of the bias and variance. So essentially we can create one data set. So this, instead of having one D, now we have D1, D2, and each of these is a data set, and from each of these we get an estimate, second estimate, and then if we have S samples, we get S different estimates. Then we can calculate the sample mean of these at a specific point, and we can calculate the sample variance. This is an estimate of the variance. That's why we have the hat here. So we calculate the sample variance, sample mean, and then the bias will be just, the bias is the expected value of the estimate minus the true function. So an estimate of the bias will be the sample mean minus the function itself. We will clarify this using an example in R. Okay. Okay. There's this is an R example illustrating just the ideas that I mentioned. Um, so we have this function here. Here I'm defining a function. So this is also a way to learn for you to define function, a simple function. We define f is a function of x, and it's an exponential function. It's a combination of two exponentials multiplied by a sinusoid. And once I plot it, you'll see why this is interesting. But anyway, this is also an example of how to define functions if you don't know. Here I set the seed. When you set the seed, then anything that you draw that is random will be the same for all of us. So it will be still random, but it will be reproducible. If you run it again, you will get the same random pattern. And that is particularly useful in debugging or in comparing results between different people who are working on the same problem. Okay, so we generate data. We generate n equal 100 data points, and then we randomly draw x's between 0 and 1 are uniform. So a random uniform random number generator, n of them, and each of them is a random number between 0 and 1. Then we sort it, and we have this sequence. So and then f is a function I defined here, so I just have the x's, and I give them as an argument. So the function goes here, and we can just plot it. Okay, so this is the relationship. This is a true, maybe line. Yeah, well, this is fine. But here you see that because we drew the x's random uniformly between 0 and 1, it just, at some places the circles are closer, some places they're further apart. But let's see, lines. Okay. All right. So anyway, this is the underlying relationship. The reason I chose it because a lot of phenomena in real life they have this. There is an increase going upshoot, and then there will, whatever it is, it's a bubble that goes down, and then it goes down, and then this is the point of 0, so it becomes neutral. But because it has some momentum, and so we go down, and before things get better, things get worse, and then slowly there was this optimism that goes up, and then um, when we realize that maybe we were too optimistic, then things become a little bit more stable. Okay, so this is an underlying trend. It's just arbitrary. I chose it. The samples that I chose, the number of samples S in the nodes is here 100. So this is S. This is S in the bias variance nodes. Okay. And we want to find the bias variance for a family of functions, models, and those are the smoothing splines, which have a degree of 2 to 20. Okay, and we create this function f hat xo, sorry, this matrix f hat xo, which is a matrix with this many columns and this many rows. And then XO is an arbitrary point. I just pick it as 0.1. You could put anything. And this is the um, noise standard deviation. Okay. So what we're doing here is that for as many samples we have this for loop, okay, in which we, for each of these I going from 1 to the samples we have, we generate data. And generating data is, this is the epsilon. So we draw a random Gaussian noise. N of them, the mean is 0, the standard deviation is O. And then we add this to the function and we generate data. So y here is not, y here is a vector. So instead of doing it one by one for all the observations, let's just call this k. Not to mistake it with the I that we use for the independent samples. Okay, so this is the data generating part. And then for all the degrees of freedom for the smoothing spline from 2 to 20, we create fits. We say, okay, this is our data, y and x bar is our data, here is our data. The degrees of freedom is dsj, j goes from 1 to the how many we have, so we're just going over all the degrees of freedom. We get the fit, and then we use this function predict. We say predict using the smoothing spline the value at xo, which is our unseen data point. Xo may not be in this, may not be among these x's, or actually these x's. Well, the x's are there are fixed, so these x's, yes. And what is the y? So we have the prediction, and we put that prediction in the kth row and the jth column of f hat xo. Okay. Then, so essentially, what we're doing is, let's see. Kth row, so we have looking at the sample 1, 1, 2, 3, the samples, and then here we have degrees of freedom. df equal 2, then we have df equal 3, df equal 20. So okay, now here what we can do is we can also plot. We plot the data in red, then we plot the true underlying curve in black, then we use the fitted one in blue, okay, and then we have a title which tells us the degrees of freedom, and then here we just have a prompt. So let's just run this. Okay, So degrees of freedom, when the degrees of freedom are 2, when degrees of freedom are 2, then, well, here you see, this is the underlying curve. This is black is the underlying trend we like to capture. It's the population signal. Red is the data. You see, it's hugely scattered. So this is a synthetic data example, so we know what's the truth, but this is very useful for illustrative purposes. Degrees of freedom is 2, so it's a line. A line has an intercept, has a slope. Now we have something quadratic, cubic. And you see, as we increase the degrees of freedom, the curve will look more and more like the underlying curve that we like to capture. But if we add the degrees of freedom too much, then suddenly the flexibility will not serve anymore to capture the true underlying trend. Rather, it starts capturing some idiosyncrasies of the noise. Just pay attention to this part. This is going up here at around 0.9. This is the idiosyncrasy of the noise. This is not the pattern that we like to capture. And when we get to degree 20, suddenly a new data will be generated from the data generating process. Just pay attention. This is going up and down here. Now I have a new data set. It's around the same trend, but it's a new data set. And again, at degree 5, 6, things look reasonable. You see, now at this point it's going down, whereas in the previous case it was going up. So this up and down, somebody might over-interpret this. This going up and down might say, oh, this is something I found in the data. No, this is noise. Well, how do we know? We will learn this. This is a big part of this course. Here's a new data set. Again, now you understand what I mean when you hear a new data from the same data generating process. And now you understand what it means to have high variability. So when the degrees of freedom are large, it seems that the estimates have a high variance, right? Because they're flexible, and when they're flexible, they try to accommodate the idiosyncrasies in the data. But we don't care about those. We care about the patterns that are there from one data to another data set. Okay. Now let's just comment this out, so this won't run. But you see, for each, so f hat xo is a matrix where each row refers to a distinct data set coming from the same data generating process, the distinct sample. Now, along that row, we have various estimates of f hat at point xo, and these various estimates are different because they come from smoothing splines with different degrees of freedom. So you see, remember here, as we change the degrees of freedom, so depending on what the degrees of freedom are, then the estimates at xo, which happen to be 0.1, will be different. It's not the same. Let me just run this again. see that at point 1, the estimate is here. As we increase the degrees of freedom, the estimate is increasing. So as we press enter and we are increasing the degrees of freedom, we are filling the first row and the first column, first row, second column, first row, third column, first row, fourth column, and we are just filling the first row with estimates of f hat xo at xo, which happen to be 0.1. Okay, so with whatever the value at 0.1 is, we are filling the first row. We're filling the first row. We're filling the first row. And then we go to degree 2. So maybe actually what I can do is I can do something else. Sample equal okay. This again. Okay, so we know which sample we're talking. Sample is our row, degree is our column, but degrees go from 2 to 20. That's why I use the index of the degree as a column. But now you see we have the first sample. Essentially, the data is the same. That's why it's the first sample, second sample. Anyway, so this will happen, and then we fill this matrix. Okay, so we fill this matrix, and then we calculate the bias squared, the variance, and the mean squared error by just combining what we have. So we do the column means. So along each column, we calculate the mean, because along each column we have different samples, right? So this gives us, this will be an expected value of f hat xo. This column means f hat xo is this part, is the sample mean. Okay, which is supposed to be an estimate of this expected value. Then we calculate the column variance among the samples, which is this part. It's the sample variance along the samples. So this one here should be this is actually k, if we want to be consistent with the okay. Okay, and then we have the mean squared error, which is just a call means between the true f and the estimate, which is it's this one. It's this quantity. It's a sample mean. This is the expectation. We look at the sample mean of this quantity. Okay, so that's the MSE. Okay, so we have the bias square, variance, MSE. We put them in a data frame. Okay, where the first column of the data frame is filled with the bias square, then followed by variance, then followed by the mean squared error, and then we add the labels, bias square, variance, and then MSE. and then we add the degrees of freedom on top of each other. So, and then we create names for the columns. The first column, because it's the value itself, it's a value. Then the second column is the measure, and the third column is the degree. So if you look at the data frame we have, it's very nice. So you have the value, we know what the value refers to the bias square degree 2. And then we go to from degree 2 to degree 20. And then we have the variance from degree 2 to degree 20. And then we have the mean squared error from 2 to 20. This is one way of putting everything in a data frame. And then we use ggplot, which comes from this library. And we just give it the data frame. We say, okay, or x is the degrees. So we want to plot the bias, variance, and mean squared error, essentially the values based on the degrees of freedom. And we want the color to be based on the name of the measure. So we want bias be different. Okay. And then we can plot it. And this is a very interesting figure. Essentially what it's saying is that as you increase the degrees of freedom, as you increase flexibility, the bias reduces. As we increase flexibility, the error that is introduced by approximating a real-life problem, which may be extremely complicated, by a much simpler model, reduces. Obviously, why? Because the model becomes more complicated, so it's able to capture this complication. At the same time, the variance increases, as we saw, because the more flexible the model becomes, it may verge on the side of capturing noise rather than signal. Another interesting thing is that the mean square error goes down and then goes up. So it's the mean square error is shaped and it's saying, okay, yes, if it's too simple, if the degrees of freedom are low, then the variance is low, yes, but the bias is high, so the mean squared error is high. And if it's too flexible, yes, the bias is almost zero, but the variance is high. So maybe somewhere in between is useful. And that's the bias variance trade-off. So, yeah, that's it.